The Indian leadership style is characterized by a particular way in which he thinks, feels, and acts. Mind you, this is not unique. For he lives and thrives in two worlds: a primary system that has 7,000 years influenced by Kal, Desh, and Patra, and a more postmodern world with leadership principles that are derived and borrowed mostly from the West. To make this clear, let me use the analogy of the NCPA theatre in Mumbai, where the Shakespearean play is being enacted. The actors are Indian, the audience are Indian, the stage is Indian, but yet Hamlet is speaking to be or not to be. And this is really the reality of the Indian context. There is a foreground and there is a background. I argue that an effective leader is one where he's able to integrate these two aspects. Otherwise, it leads to contradiction, paradoxes, polarities, what we call as dharam sankatas. I assert that we need a blend of both the Harvard and the Rishi to create the Rajeshri model. A model that includes diversity, inclusion, ecological balance, ahimsa, that the world is one family. I hope this book allows you to explore your own personal leadership and discover the leader in you. Thank you.
Good evening and welcome back to Studio One. For our next session, we are very happy to have with us the panelists of the Mysteries of Cosmos and Us. For our first panelist, Dr. Shohini Ghosh is an award-winning theoretical physicist and a professor of physics and computer science at Wilfrid Laurier University in Canada. She and her colleagues were the first to experimentally find a connection between chaos theory and quantum entanglement. Dr. Ghosh is an expert in quantum physics and serves as co-editor of Canadian Journal of Physics. She is a TED Senior Fellow and a TED speaker. Our second speaker is Dr. Peter Altman. Dr. Peter Altman is trained as a biochemist and now works as a science writer and speaker. His areas of special interest include cosmology, biochemistry, and photography. He is the founder and chairman of the Bricket Wood Science Group and a member of the Magic Circle in London. This session will be moderated by Radhika Raje. Radhika Raje heads the marketing team at one of India's leading publishing houses, Jaco Publishing House. After being involved editorially in newspapers like Free Press Journal and magazines like Time Out India and Man's World, Radhika has opted to work with books and to promote reading as a culture through various offline and online platforms. Over to you, ma'am.
Thank you, Rahul. Hello everybody. Hi Shohini, hi Peter.
Hello.
Hi. It's so good to actually get on here and speak to both of you. Before we begin our session, I would like to thank PILF team for arranging this amazing online festival for us and giving us a platform to speak about books. Now that we begin, I would like to first, speak about how our association started. How all there's one thing that's common between all three of us, which is JECO. So I'm very happy on behalf of JECO. I would like to thank both of you, to be a part of the session as well. So let's just straight away dive into this session and begin so that, because there's so much that we need to talk about. As we begin this session, first thing that I really want to ask is what exactly do you think is a process that the world is going to end? Because 2020 definitely felt like it's coming to an end. It looked like world is going to just completely crumble this year, but clearly we are all here right now. So that is something that I thought, we could begin with, that you both can talk about. And speaking of beginning, you can also maybe share what was the beginning of the universe, and as the most commonly known term, which is Big Bang Theory. So if you both could just share some light on these topics first.
Shahini, after you.
Okay, thanks so much, Veera, and thanks, Radhika, for hosting this session. Wow, beginning and end of the universe. I'll start with the beginning, although I know, Radhika, you mentioned the end. It's probably flows better if we talk about the beginning. So you know how in all these Marvel superhero movies, we always have this origin story for how did Iron Man come to be, or how did Captain America come to be, and so on. So actually, we also have an origin story for the entire universe, and that's what we call the Big Bang Theory.
Right.
Although, of course, most people know it as a TV show. The good thing about the TV show is that the intro, the little song that used to be the introducing music for the Big Bang was actually correct. It actually described how the universe came to be, and it's the best fitting model to the evidence we have. So,
Right.
and really, essentially, what it says is that, about 14 billion years ago, the universe had a beginning. So it's not like the universe has been, in the form that we know of it, has always existed. It started at a moment about 14 billion years ago. And since then, there has been a huge expansion of matter and energy. And that expansion is still happening. And during the whole process, not only was there an expansion, everything started from a very hot, dense point. And then as it expanded, it cooled. And then gravity, matter, of course, started clumping together thanks to gravity. And stars formed, galaxies, all of the structures we see today. Eventually, our sun formed, and that was about 5 billion years ago. Since then, the universe has kept on evolving. Its story continues, and eventually there will be an end. And we don't quite know what is the end.
Right.
So it's kind of like having that next exciting episode in the Marvel superhero movie, right? We don't know the end or what's the next one. But we have some ideas. And so there's different options depending on whether the expansion will slow down or stay the same or speed up. So and that depends on how much matter there is in the universe. So by gathering more and more information about matter and energy and the expansion rates of the universe, we can try to get a better idea of whether we're going to keep expanding forever or eventually slow down, and then perhaps we'll collapse and there'll be a huge big crunch to end the story of the Big Bang. So that's where we stand today.
Peter, you want to share some light on this mystery as well?
Well, the first thing I'd say is I think it's a shame it's called the Big Bang Theory, because that implies that it's not established fact. A better name would be the Big Bang Event, I think. The inevitable question, of course, is that's all very well, but where did all the stuff come from to create the Big Bang? And I don't have a problem with saying, well, we don't know, because there are lots of things that we don't know about. And I have an analogy that I actually mention in my book of a card trick. And I performed the trick and I put it on YouTube, and there's a link in the book. And the point of that is that you look at the card trick and you think, well, that's good. I wonder how that was done. And you probably won't know how it's done. But that doesn't cause you a difficulty because you know it's a trick. You've seen it happen, but you don't know how it's done. And the same with, I think, the origin of all the matter in the universe. You could say, well, we don't know, but that doesn't matter that you don't know. It doesn't mean that there isn't a logical explanation that obeys the laws of nature. It just means that we haven't found it yet. And I don't have a difficulty with that. As to the end, I suppose the same thing applies to the end. You don't know how it's going to end. We haven't got there yet, so we'll have to wait and see, won't we?
I guess so. I don't think anybody's in a hurry to see really how it's going to end.
It'll be a while.
I really hope so. While I'm sure it will take a lot of time to actually come to an end, because I don't know what the concept of time itself is. And, you know, because we're also struggling with a lot of concepts like time travel, you know, in general. There are a lot of books, there are a lot of movies that have tried to explain it. But obviously it's a very blurred concept in people's head. So maybe we could speak a little about time travel, and you can tell us what exactly is it, and if it's possible even.
Well, okay, I mean, time travel has been a beloved subject of science fiction writers for a long time, and popularized by H.G. Wells in 1895 with his book, The Time Machine. So there are two types of time travel. You can go backwards or you can go forwards.
Right.
So if we talk about backwards first, it's possible to look back in time. Actually, it's more than possible, it's inevitable, because light has a finite speed. So when you look at your watch to see the time, you're actually seeing the time about a billionth of a second earlier than it really is, because later than it is, because that's the time the light has taken to travel to your eyes. Makes no difference in practical terms, of course, but if you look up at the sky, you're seeing things that are a long, long way away. Now, there's a galaxy called M109, and I chose that one because it's about 80 million light years away. That means that light's taken 80 million years to travel from the galaxy to us.
Right.
And the same would be in reverse. So if you imagine an alien astronomer sitting on a planet in the M109 galaxy with some super powerful telescope and looking at Earth, my slide will show what he might see. If I could have my slide, please. It'll only take 80 million years to arrive. Is this not going to happen?
Oh, okay.
Can we have the slide, please? Yeah.
Fine, thank you. Brilliant. So yes, dinosaurs. He, she, or it would see dinosaurs roaming around the Earth. Why? Because 80 million years ago, there were dinosaurs roaming around the Earth. And that astronomer would be seeing things that happened 80 million years ago, because that's how long the light's taken to travel from the Earth back to his telescope. Okay, we can lose the slide. Thank you. So looking back in time is easy. It happens all the time. Can we lose the slide, please? Thank you. What about traveling back in time? Well, there we have a problem, because there's a thing called the grandfather paradox. I don't know why they picked on grandfathers, but whoever did it. The idea is that if you could travel back in time and you killed your grandfather, then your father wouldn't have been born and you wouldn't have been born. Therefore, you couldn't travel back in time and do it. And it's hard to resolve that paradox, which sort of implies it's one of many so-called thought experiments. No one's done it, obviously, but you just think about it. That means that you can't travel back in time. Also, if you could, why aren't there any people here from the future? So I think traveling back in time is not possible. Now, what about traveling into the future? Well, one of the consequences of Einstein's relativity equations is that the faster you travel, time slows down. Now, in practical terms, it doesn't make much difference. Driving down the motorway at 60 miles an hour, it will slow down, but you won't notice it. But people on the International Space Station, it's been worked out that the time there is 1/100th of a second slower over the period of a year than it is on Earth. Again, it doesn't make much difference, but if one day one could travel close to light speed, 99.999% of the speed of light, then 1 year for you on your spacecraft would be equivalent to about 1,000 years of people back at mission control on Earth. So if you could whiz around the solar system for a year at very close to the speed of light, you would get back home 1,000 years after you left. In other words, you've traveled into the future. The downside, though, is that you can't go back. So traveling into the future, I suppose, and Shahini will say if that's right or not, is allowed for by physics, but it's a one-way journey. And that's it.
Do you agree to this, Shoini?
Sure. I think that was great what Peter explained. It is absolutely the way the laws of physics work, which we cannot violate as far as we know. I guess I'll add a couple of things. One is, yes, this idea of traveling faster and therefore being able to, be back on Earth. You're at a much later time, 1,000 years in the future. The thing is, you cannot go back into your own future. I mean, you can't travel into your own future, I should say. So, and this is what we all want to know, right? What's going to happen?
Absolutely.
Right? 10 years down the time, we can't do that. So that's the one thing. And the other thing is, a couple more things I want to mention. To talk about going back in time or looking back in time, which is what Peter mentioned. We have fantastic time travel devices to do that. That's what we call telescopes. So what's fantastic is that we can actually look at any moment almost in the entire history of the universe. So for example, if we want to know what the universe or a star looked like maybe 1 billion years after the Big Bang. Right. What we would want to do is look out to a distant galaxy that would take maybe, it's so far away that it would take about 12 billion years for the light to get to us, which means that by the time it got to us, what we're seeing is the galaxy after 1 billion years after the universe started, because since the universe is about 14 billion years old, then we're seeing the universe as it was just 1 billion years after the universe. So we can pick any age of the universe, and as long as we look far enough outwards with our time travel devices, which is our telescopes, we can literally map out the entire history of the universe and actually see it through our telescope. So that's kind of beautiful. But also the idea of whether we can actually ourselves physically travel, we can look back in time. Can we travel back or forward in time? Well, technically, Einstein's general theory of relativity allows this idea, because in Einstein's theory, the universe, all of space and time is like this folding fabric. It can bend and it can warp. And what causes that is essentially matter. So if you have enough highly dense matter, then in fact you have these folds. And in fact, we are part of this kind of folded fabric of space-time. This is why, for example, the Earth actually is trapped inside this folded, what we call the gravity well of the sun, because there's this sort of path that we cannot escape from, because there is this folding of the space-time. Now, if we had a very, very, very dense part of the space-time, so matter that is so dense that it folds it much more than the sun can, then it might actually cause the entire fold to be so strong that it folds on itself and creates what we call a loop. And that can be a closed loop, not just in space. sort of like how you can fold a paper so that the two corners touch each other. So different parts of space can touch. Whereas instead of thinking of it as space, you can fold time so that different parts of time touch. So technically allowed by the laws of physics, but that's mathematics. Those are what the equations predict. What Peter said is, of course, it's very important that if that's possible and you fold time and go back, what if you go back to the point where you end up accidentally or deliberately ending your own ancestry? That's a paradox, and the universe makes paradoxes. So the question is, why or why not? As in, is there a way to resolve the paradox so it never happens and still be able to fold time? Or is it just not allowed and we haven't figured out what is the law of nature that prevents the paradox? But one way or the other, it's an interesting open question, actually.
Yeah, so I guess we just have to wait to find this answer as well.
Yeah, and lots of people are working on it. In fact, there was some recent research that claims that if you look at the equations, they found solutions which seem to resolve the paradox, meaning you can find a way to make things work out so that there's always a solution. This is all mathematics, of course. There's always a solution that avoids the paradox. So that's kind of very exciting, interesting work.
And this is an ongoing research right now.
Yes.
It's ongoing.
Yes, of course.
Awesome.
No time machines actually being built as of now, other than telescopes.
Oh, damn.
I know, right? Too bad.
That's bad. While you're talking about time machine to meet either the past us or future us, there was another question that we also had in mind is if there is life other than on our Earth, if there is life on other planets, is there anything that's proven that there is a life? Peter, I think you've addressed this in your book as well. So I just wanted to know if you think there is a life on other planets, and is there a way to interact with these people, if I might say?
Well, it's a really interesting question. It's probably one of the most interesting questions that one can ask. So the way I look at it is that astronomers have worked out roughly how many stars there are in our galaxy. And they've also worked out roughly how many galaxies there are in the observable universe. And the Kepler telescope has given some good numbers as to how many stars have planets around them. So if you multiply all those numbers together, you end up with a number that is probably roughly in the ballpark of how many planets there are in the universe. And that number is something like 10 to the power of 21. That's 1,000 million planets. That's a lot of planets.
Right.
And that has led many people, including some very eminent scientists, one of whom was the late Professor Stephen Hawking, who wrote, and I will just read this. He said, given the thousands of Earth-like planets outside the solar system, on purely statistical grounds, life almost certainly exists somewhere else.
Okay.
Now, with all due respect to Professor Hawking, I have to say, I actually think he's wrong. And the reason I say that is that although the potential number of planets is admittedly huge and very impressive, the problem is that we don't know how likely it is that life will arise. So here I have a container with some raffle tickets. And I'm going to take one out. It's number 147. But Hika, what are the chances that I would have chosen or picked out number 147?
I don't know. I'm not sure.
Why not? Why don't you know?
Because I'm not sure how many numbers are there in your
Exactly.
container.
You don't know how many tickets are in the drum. It could be 100, it could be 100 million. And therefore you
Absolutely.
can't work out the odds. We don't know what the odds were of life having arisen on Earth. It required lots of things to be right. Temperature, pressure, atmosphere, all sorts of things had to be in the right position at the right time, at the right temperature, at the right pressure, etc.
Right.
And we can't work out the odds. It may have been 1 in 10 to the 21. It may have been 1 in 10 to the 100. And because we don't know the odds, we're not entitled to say that the admittedly huge numbers of planets in the universe were enough for life to have arisen anywhere else. All we know is that it's possible because here we are, but we don't know how likely it was. And to say that on statistical grounds, you're not entitled to say that because you don't know the statistics.
Right.
So my personal view is that unless evidence to the contrary appears, and I'll say something about that in a moment, I think that we are alone in the universe. Now, a couple of months ago, some research was published about the discovery of phosphine gas in the atmosphere of Venus.
Yes. Yes.
Phosphine gas is produced by various microbes on Earth, but it's quite hard to make it by other natural processes because it requires a lot of pressure and other special conditions. And as far as is known, those conditions do not exist in the atmosphere of Venus. Now, the discovery of the phosphine was spectroscopically, and they found one spectroscopic line that they said indicated phosphine. So the first thing is that that discovery needs to be confirmed, that it really is phosphine.
Oh, okay.
Secondly, it needs to be confirmed that there's not some exotic chemistry on the surface of Venus that produced it.
Right.
Thirdly, it needs to be confirmed that there are living microbes in the atmosphere, which would require probably a sample return to Earth. But there have been, I think, 38 probes sent to Venus since the 1960s. So it needs to be shown that any microbes that might be there are not contaminants from other missions that have come from Earth. So a lot of work needs to be done, but it's a potentially exciting finding. So we'll have to wait and see what that produces.
Right.
The question as to whether we could ever communicate, SETI was set up by Professor Drake in 1961 to communicate or try and communicate with other alien civilizations by radio waves. But as we were saying before, the distances are so enormous that any two-way communication could take millions of years, which just isn't going to happen. The furthest probe that's ever been sent from Earth is Voyager 1, which was launched in 1977. It's been going for 43 years, still sending back data. It's traveled 14 billion miles. Now that sounds a long way.
Yes.
It's 1/2000th of the distance to our nearest star system, Alpha Centauri. And if it was pointed in that direction, which it isn't, but if it was, it would take 86,000 years to get there. And that's the nearest star, only 4 light years away. So unless Shohini can tell us that there is a way of exceeding the universal speed limit of the speed of light, I just don't see any practical way of communicating with any other civilization should it exist.
So, yeah, Shohini, sorry, you were saying something.
Oh, no, I was just going to say, I don't know, Peter, of any such mode of communication. As I said, there's some very, very probably unlikely possibility of being able to create these shortcuts through space-time I was talking about, or these so-called wormholes. But creating that would require us to actually be able to, for example, create matter and make it so dense that it would be, like shrinking the sun to the size of of a tiny, like sort of grain of rice, for example. So that's not going to happen anytime soon. If we think we have energy problems now, imagine the energy required to do things like that.
Yeah.
So yes, I think the universe, even if there is life out there, and even if it is teeming with life, we may never actually be able to communicate in real time with them, which, the universe has this very cruel sense of humor. We have access, we can know about what's out there, but we may not be able to connect with them.
Sure. There's also the thing called the Fermi Paradox, which was came from Enrico Fermi, the Nobel Prize winner in the 1950s. And what he said was, if the universe is teeming with life, then why haven't we heard from them? Because some of them would have had billions of years of development over us. There are stars out there that are, as Srini was saying, 12, 13 billion years old. If they've got planets around them, they've got 6 or 7 billion years of extra evolution and technological advancement ahead of us. So if there is a way around these problems, they should have solved them by now. But we haven't heard from anybody. And that was his interpretation and reasoning for saying that we are alone.
Right. Shoini, just to add further to your statement saying how cruel universe is, and I think from what I've read about universes, I think the most cruelest term or the most cruelest concept that I've come across is a black hole, where it can completely just take it all in and make everything just disappear. Is that exactly what a black hole is?
Yeah, so a black hole is sort of related to what I was talking about before, these, sort of gravity wells, deep folds in space-time. In fact, the deepest you could go is, imagine if it was an infinite well. So a black hole is, one way to imagine it is like, let's say you're trapped in a well. I hope you're not, but in case for some reason you are and you want to get a message out because you can't climb out. So you write something on a piece of paper and you crumple it up and you throw it. Yeah. But you have to make sure that you throw it with enough energy that it's fast enough so that it can escape your particular well, right? And imagine if you're in a deeper well, you gotta have even greater speed with which you throw it, right? And if it's even deeper, then that keeps increasing, right? So that speed with which you have to throw to be able to get out of the well is what we call the escape velocity. Now imagine you're in a well that is so deep that this velocity with which you have to throw your message is greater than the speed of light. It's not possible because turns out nothing can go faster than the speed of light, and that is part of what emerges from Einstein's special theory of relativity. Turns out there are objects, or as I said, these particular sort of folded gravity wells in space-time that are so deep that the escape velocity is greater than the speed of light, so even light cannot escape, and hence the term black hole. Yeah, and they do actually exist because they have been discovered. Sorry?
It is the most intriguing one for sure. Like, I think there is a lot of curiosity where black hole is concerned.
Absolutely. So I think there's many reasons for it. One is it felt like science fiction. Even Einstein, when who of course developed the theory of relativity, which led to the idea of the geometry of space-time and curvature and so on, he did know about these particular solutions to his equations, which are what we call singularities, meaning these infinite points, right? Infinitely deep points. And he didn't think they were real because they, when you look at, let's say it's like when you're doing mathematics and you have a divide by 0, there's something wrong there, right? It's not real. So for him, that was what this kind of singularity was, like a divide by 0 problem, meaning it's not real. It's not like the universe actually divides by 0. It's just something in the math. So even he didn't believe that they were actually possible, actual objects in the universe. But in the 60s, in fact, there was a lot of mathematical research done on this, and it was proved that if the rest of the theory works the way it does, and there's lots of actual physical observations that confirm relativity over the years, it keeps getting confirmed more and more. So in the 60s already, it was known that these are not just artifacts of the mathematics. It's not a divide by 0 error. These are actually real generic solutions. And in fact, Roger Penrose, who was involved in that kind of work with Stephen Hawking, got the Nobel Prize in 2020 for exactly showing that these are not divide by zero errors. These are actual real solutions. And very soon after that, after all of this was developed and the framework became really solid and robust and mathematically, in the 70s, early 70s, by 1971, the first black hole had actually already been observed. And I was very excited because, when I learned about black holes, I realized the first one was discovered by an astronomer based in Canada, which is where I am now. So yes, it's very exciting. It's actually about an hour and a half away from where I am right now. So yeah, it's since that time, there's been a lot of these kinds of discoveries. And the second half of the Nobel Prize in 2020 was to another team involving Andrea Ghez, who is an astronomer who does actual observations of the center of the Milky Way. And she was able to map out the orbits of stars around this center. And of course, the way stars move depend on what it is that they're orbiting, right? And by looking at the actual paths of those orbits, she could figure out that this thing in the center of the Milky Way it's so massive that it can't be anything but what we call a supermassive black hole. Right. So that was why she got to in the second half of the Nobel Prize with her partner, Kenzo. Yeah. So it's quite a fascinating story of discovery to know that these things that seem like they shouldn't exist. Even people like Einstein felt that they were an anomaly. They do exist. The other reason they are fascinating is because although we understand that they exist, because there is this question of what we call the singularity, it's not clear what is the physics of that applies inside the boundary of the black hole, because we don't have a way to describe something where we're talking about a lot of matter that is compressed to sizes that are actually microscopic. Because at the microscopic level, the laws of physics that we know apply are described by what we call quantum physics. Correct. And at the macroscopic level, we have relativity because, massive stars and planets, and it works very well at that scale. And now we have to find a way to combine relativity with quantum physics to be able to understand huge amounts of matter in tiny little spaces. And nobody has cracked that as yet. So that's probably one of the big questions that we need to answer in order to understand things like black holes. So,
wow. I was just noticing all the references that you both were using. He used Stephen Hawking, you used Einstein, you used Roger. It took you a while to actually get to a woman scientist, like where the references were concerned. Is it really a male-dominated field? Or it's just that the women are not known for their discoveries as much as male are. I'm just very curious to know as to what can, because in India, science as a field, it's huge. Like there are a lot of people who want to pursue science, but most of them don't understand what the route is, and especially with women, it becomes tricky, I assume. So I just wanted to know what your views, since you both are in this field, what your views are, depending on what the women scientists are doing. Are they doing anything wrong, per se, to not be recognized? Or was it just a bad timing a few years ago and it's evolving now? So just your views on that.
Well,
whoever wants to go first.
I think it's true that science has been a male-dominated topic for a long time. There have been some very well-known women scientists in the past. I'll just mention two, because at the time that they were working, they did amazing groundbreaking work, these two, but they were never recognized for it. So the first one I'll mention is Rosalind Franklin, who was involved with DNA. Now, DNA was discovered in 1869, but it was in the 50s that Watson and Crick and other people were trying to work out the structure of the molecule, because no one knew how it worked and how it passed on genetic information. And the way they were doing this was to make crystals of pure DNA, fire X-rays at it, and you get what's called an X-ray diffraction pattern. And if you know what you're looking at, you can work out the structure of the molecule. And then they built models. But their DNA wasn't pure enough to get good pictures. And Rosalind Franklin, who was working at King's College in London, she was a very meticulous worker, and she made some of the purest DNA crystals that had ever been made. And her X-ray diffraction photographs were so good that it was possible to deduce the molecular structure. And what happened was that her boss, Maurice Wilkins, showed Watson and Crick her photographs, the one that's become known as Photograph 51, as made into a play not long ago. She didn't know this, and he shouldn't have done that. As soon as they saw it, said, yes, it's a double helix, because they knew what they were looking at.
Right.
And she never got the credit she deserved for that. They won the Nobel Prize for Physiology and Medicine in 1962. She died a few years earlier from ovarian cancer. And it's only in more recent years that she's been acknowledged. I think there's a satellite going to be named after her, or a probe or something.
Yeah.
A great scientist, a brilliant scientist who was never recognized. And the other lady I mentioned was Henrietta Leavitt, who was working at the turn of the 1900, 1910 or so at, I think, Mount Wilson Observatory in America. And her job was to catalogue stars from the photographs taken at the observatory. So a boring job, but she was meticulous at it, and she spent a lot of time doing this. And she found some certain stars they're called Cepheid variables, and they get brighter and dimmer over relatively short periods, hours or days or sometimes weeks. And she found that the brighter and dimmer they got, that was related to the time between the cycle of dim and bright. And the ones that got brighter had a shorter period, and the ones that got not so bright had a longer period. And all of this enabled her to work out a method of how far away they were. Now, the topic of how do astronomers measure distance, you want to measure distance, the length of your desk, you get out a tape measure, or how far it is to the restaurant in the town. You look at the odometer on your on your car, the dial in your car. How do you measure the distance to a galaxy? Interesting topic. Won't go into that now, but what she did paved the way for that to become possible. And like Franklin and other female scientists later on, she never got the credit while she was alive. But there have been some brilliant female scientists, but in the past, unfortunately, they were never given the credit because they were women.
Right. Which is extremely sad.
Yeah, very sad. Very sad.
Yeah. How has your experience been, Shoini, since you've been in the field? Have you faced anything where you thought that women are not getting their credit, or they were not given their due as much?
Sure. So personally, it's true that certainly in my classrooms, I was often the only woman, to the point where I've had professors who walked in and said, "Good morning, gentlemen." And so, I always used to say, "Hey, look, I'm like Harry Potter. I have my invisibility superpower, right?" So, and these kinds of, it may seem minor, but over time, if you feel isolated, you sort of start wondering whether you should even be in that classroom, and whether you fit in, and do you have the skill set. So I think there's a lot of that kind of perceptional and sort of environmental bias still happening. And it's a hard thing to make change, but it is possible. And so I feel like things have changed, and it's not just that today we have more women working certainly in physics, but also in all the other sciences. Just to sort of say what Peter was saying, that there have been women who've contributed in all areas, also physics, throughout history, from all over the world. The reason that we don't know about them is because they haven't been given credit, as Peter was saying. So for me, one of the really important reasons I wanted to write my book, Close to the Cosmos, was to tell the story of all these major physics discoveries, but to include everybody who's contributed, which includes lots of women, in fact. So I'm very proud to say that actually every chapter in the book, each chapter deals with a different discovery, like relativity or quantum physics, or what is light and so on. And each of those chapters does include huge contributions by women. And I'll mention one who I hope is celebrated more and more in India over the years. She was a brilliant physicist. Her name was Bibha Chaudhary. And she was involved in work where she developed methods to identify particles in the atmosphere. So we have all these high energy cosmic rays that hit the atmosphere, and they create other particles. And some of them are these fundamental particles of the universe. And so she had used techniques that she and her mentor had developed to be able to identify brand new particles, fundamental particles in the universe. And those, but they couldn't confirm the work because she didn't have enough equipment. This was in the 40s. And then a few years later, the British scientist Cecil Powell confirmed those discoveries and won a Nobel Prize. And he did acknowledge Bibha Chaudhary's work and Bose's work, who she worked with. But I don't think she's been given the kind of credit that she deserves. And there's a lot more to her story. And I encourage everybody to do a search for Bibha Chaudhary and many other women like her. And if you want to know about other women too, there's so many stories that are really fascinating, and many of them are in the book.
Right. So I think we are coming to the end of the session. Do you want to just take a minute to speak about your book, now that you've mentioned it? And then we'll go to a minute for Peter's book as well.
Sure. As I said, the book is really, for me, it's about exploring the ultimate mystery, which is, how does the universe work? All of the major discoveries we've made, but not just what the science is for what is relativity, what is quantum physics, what is the standard model of particle physics. It's not just about the science, but how did we get there? It's not like one day Einstein woke up and said, here is relativity. Science doesn't work like that. There's a long process. And it's very much like what detectives do when they are trying to solve a mystery. You have to collect evidence and data and then try to fit a model to it and then test it and see if it's really correct or not. And it's an evolving story. So that's what the book is about, and about all the many people who do that kind of work.
All right. Peter, why don't you also share your book information with us?
Yeah, why not? Thank you. This is a proof copy of it. So it's called Mysteries of the Universe, Answerable and Unanswerable Questions. So what I've done here, in the book, there are 14 questions. Some of them we've addressed today. Does alien life exist? Is time travel possible? Others are, how did the universe begin? How will it end? How old are the Earth and the universe? Is the future predetermined? So each chapter is actually formed as a question. I then discuss the evidence for the question. And if at the end of it, in my opinion, there is an answer, like how old is the Earth? Well, we know that, so there's an answer. Most of them don't have an answer because there's not enough evidence. So I get what I've called my personal best guess answer. So that's what the book is. I've illustrated it quite well. There's nearly 200 illustrations, photographs and diagrams and things to help understand the flow. And at the end, there's an appendix on what I was saying, how do astronomers measure distance? It's a bit mathematical and you don't have to read it, but it's there for those who want. And then right at the end, there's a free gift. I won't tell you what it is, but it's a thank you for people who have decided to buy the book. The paperback will be out, I hope, next year. There is an ebook and there's also an audio book. You'll need to be brave to have the audio book. It runs for nearly 10 hours. I also, no one's ever heard of me. And to get a book published by an unknown author is a very, very difficult task indeed. And I really want to thank Jaco for having faith in me and for agreeing to publish it. You've been great. Thank you.
Jaco is very happy that both of you are part of Jaco now. So it's a great opportunity for Jaiko as well.
Well, I'm very grateful. Thank you.
Thank you. We'll just move to the questions. I think we have some questions. Yes, let's begin with the question. This is the first question on screen.
I think that's one for Shahini.
We actually, if you want to talk about the Earth itself, from a physics point of view, we know exactly how it's going to end. Unfortunately, it'll be swallowed up by the sun, because at some point the sun is going to run out of hydrogen fuel, which is part of what is happening right now in the sun. There's in the core of the sun, there's nuclear fusion happening. So it's this giant fusion reactor. And that's what's creating all the energy. And what it's using in the reactor as fuel for the fusion process is hydrogen, which is, of course, the most common element in the universe. But eventually it will run out, the sun will run out of hydrogen. And that'll become the beginning of what's called, it's sort of like its death cycle. And interestingly, stars have a really fascinating death cycle where they don't just stop burning and that's it. They just sort of try to keep restarting the fusion using other elements like helium and heavier and heavier elements. So they keep, it's almost like they breathe in and out. So they'll expand and contract because there are all these different forces at work in the sun. But as it starts this expansion process, eventually it's just going to get obviously hotter and hotter on Earth. So we think climate change is bad now. It's going to be nothing compared to if we survive, for the next 5 billion years, by which time the sun will be running out of hydrogen. It's already too late. We better make plans to be leaving because it's the oceans are literally going to boil. And the sun itself in size will become so big, it'll engulf the entire orbit of the Earth. The size of the sun will be bigger than that. So is that a whimper or a bang? I don't know, but it's the end. And so the Earth is doomed in 5 billion years. So get ready to make plans for that now, I guess.
Of course, what we could do, as the sun gets bigger and hotter, and as you say, Earth gets engulfed, we could perhaps all move to one of the icy moons of Jupiter or Saturn, which are going to be a lot warmer than they are now. That might
For sure.
Another 1 billion years or more to think about future developments after that.
But we can't stay too long there either, because if that dying star will eventually become fully dead and will end up a cold remnant. So we might want to find another living star.
Yes, we should. I think there's a lot of research going on that as well.
Yeah, there's a few stars out there. So
we'll just take our next question. How does vacuum or nothingness have volume and occupy space? Does the secret of the universe lie in deciphering it?
That's a deep philosophical question, I feel. But no, I'd say that the physics answer is that vacuum is space, right? So, when we talk about things like the Big Bang and creating the universe, it's literally expanding the space-time itself. The expansion of the universe is not some matter that's now getting spread out over space that already exists. No, space-time itself is the expansion. And I think there's now newer theories which are trying to understand this very deep question of what is space-time itself. We understand that things like matter can fold space, and folded space influences how matter moves. These are like describing what the universe is, but why is it behaving that way is another layer. And some very interesting answers are now coming from quantum physics, where it may be that the structure of space-time itself, which of course includes what we call vacuum, is based on an idea called entanglement, which is very peculiar and bizarre, and I won't get into the details. There's details in my book, so I'll leave it at that. But it is actually a very interesting open question. Why is it that space-time, this interesting fabric structure of the universe. Why does it exist the way it does? It's an open question.
All right. We'll
Peter.
move on to one. Yes, Peter.
I think that there probably are more laws of physics still to be discovered. Dark matter, dark energy, what are those concepts? How is it that as the universe expands, it isn't really that the galaxies are moving further away, it's the space between them that's expanding, and even that can be faster than the speed of light. So there are a lot of things still to be discovered. So who knows what might be possible in years to come when these things have been sorted out. Very exciting time.
And to add to that, you're right. In fact, what we know, the known sort of ordinary matter of the universe is only 5%. We know how little we know. We know that dark matter, dark energy is 95% of the universe, and we have no idea what it is. So that's how much more work we need to do.
All right. Now we'll move on to our next question. Is it true that the sound of the universe sounds like Om?
Another, I think, more philosophical question. So the fact is, if you're out in space, light can travel through a vacuum, but sound cannot. So actually, it's completely silent in outer space. And all those science fiction movies, I always laugh because they show all these great battles and cool sounds and lasers that are whizzing by. Yeah, it would be totally quiet, except there's some air released from explosions, and that, inside explosion, you might be able to hear the sound of the explosion, but you probably wouldn't survive it. So, no.
All right. Do we have more questions? I'll just quickly check. Yes, this is the last question. Do you think that we have pockets of intelligent life considering the scale of time on the universal level?
Peter, this one's for you.
Personally, I don't, but that's just a personal view based on the fact that I think the emergence of life was such a very unlikely event that it's probably never happened before or again. But there's no evidence one way or the other for that, so that's just my personal view. Others will, as I've said, will disagree about that. I hope that I'm wrong about that, and I would love in my lifetime to have evidence that there is intelligent life elsewhere. Just imagine what we could possibly learn if there's a way of communicating. Is their biochemistry the same as ours, or have they found other ways of passing on genetics? And all sorts of fascinating questions would arise. But I don't think that is the case. It's my personal view.
Shwani, you want to add something to this?
I agree that there isn't enough evidence. Perhaps I'm more of an optimist, and so I think there's life out there. I like to go back to something I remember reading in one of Carl Sagan's books, Contact, right? Where the main scientist in that book, the scientist character, who's a woman, which I really love too, he was asked too, there's life out there, and her answer always was, if there isn't, it's an awful waste of space.
Which is so true. I think that sums up our session. It was a great talk. I thank you so much for agreeing to do this session. Thanks for being a part of Pune Lit Fest and being a part of JECO as well. And thanks to PILF as well for arranging this session. Thanks a lot.
Thank you, Radhika.
Thanks
very much. Bye-bye.
Bye.
Thank you for such an informative and refreshing session. Our last session and the next session for the day is brought to you by Picture Perfect. The session, Adapting Literature for the Screen versus Creating Original Content, begins in a short while. Join us for the same at 9:15 p.m.